Good evening, class. Today's objective is learning how to write and graph an exponential function from a word problem. So here are some notes for you to read over. I'm going to highlight a few things here that you need to know. First of all, an exponential function, the type that we're going to be writing, are going to look like this. Y equals A. Remember, that's our vertical stretch or compression times b to the x power. Now each part of this function is going to tell you something different, and we're going to get to that in just a moment. First of all, some rules. The a value, if we're having a decay, and you can see the graph, it's decreasing dramatically when you have a decay. The a value is going to be greater than 1, and b is between 0 and 1. Okay? So in this case, when you're in this format here, a is going to represent your y-intercept. Right here, your y-intercept. And then b, since b is between 0 and 1.5, we have a decay. So this is an example of a decay. Now an example of a growth. Okay, we have our function y equals a times b to the x, where a is greater than 0. Now a needs to be greater than 0 because if a was 0, the function would go to 0, and we do not want that. Or if a is less than 0, if it's negative, then our function would be negative. To have a growth, b is greater than 1. So here we have a y-intercept of 1, which you can't see very well, but that's going to be about right in here. And notice the dramatic growth. So the growth here is 2. So basically it's doubling each time. If you look at the points here, you can see the doubling at 2,000. So if we go one more unit over, we're at 4,000. If we go one more unit over, we're at 8,000. If we go one more unit over, if you double 8, you're at 16,000. So it's growing. It's actually doubling each time. Whereas in the decay problem, it's being cut in half. So notice that when we're at 100, if we go over 1 unit, now we're at 50. 1/2 of 100 is 50. Half of 50 is 25. Half of 25 is 12.5, and so on. So it's decaying by 50%. Whereas here, it's growing by 100%. So when you're writing an equation from a problem, you're going to be using this formula here. So any quantity that grows or decays by a fixed percent at regular intervals is said to possess exponential growth or exponential decay. When a quantity grows by a fixed percent at regular intervals in an applied situation, the pattern can be represented by these two functions. So A is going to represent the amount after the growth/decay. That's the ending amount. Lowercase a is the initial amount before growth or decay. So, for example, up here in this decay, our initial amount when x is 0 is 100. So 100 would be in for A, actually in this one. And then R represents the rate of growth / decay. Very important, rate. And then T is the time period. So after 1 year, after 2 years, whatever that time period might be that you're trying to calculate. So here's an example, a banking example of growth. So a bank account balance B for an account starting with S dollars, earning an annual interest rate R, and left untouched for N years can be calculated as this equation. Find a bank account balance to the nearest dollar if the account starts with 100. So very important, it's starting with 100. So that is going to be our initial amount. Has an annual rate of 4%. That's going to be our rate. And the money left in the account for 12 years. And so that's going to be our time. So notice our initial amount, $100, went in for A. 4% got changed to a decimal. If you forgot how to change a percent to a decimal, you would just divide it by 100. That went in for R. And then time is 12, and so that went in for T. Or in this case, they use the letter N. And then you just do this in your calculator, and then the amount that you end up with. So if you started off with 100, and we are growing, okay, because we're earning an interest rate right up here. We're earning. So we're earning money. That means we're increasing. And that's why we use the plus in here. We're earning 4% on our money for 12 years. So in 12 years at 4%, we've earned $160. Please make sure you use a label. In this case, it's money, so we would use a $sign. So I expect you guys to kind of read through these examples. I'm not going to read through each one of them for you. Please read through. Another growth example, a doubling example, decaying by half, and half-life decay. Look at those over. Okay, so let's take a look at another example. So we have, upon graduating from college, Ashley took a job with a starting salary of $40,000. She can expect a 6% raise in pay each year. Calculate her salary for the first 4 years. So obviously, her starting salary is $40,000. So at year 0, so no time has passed, they started her off at $40,000. So this is going to go in for our starting amount, our initial amount. Notice in the problem that we are increasing because she's getting a raise. So each year her salary is going to increase. So we're going to want to use the equation for an increase or a growth. So I'm going to go ahead and use this equation right here. So our initial amount is $40,000, which would go right in here for A. and it's going to be an increase, so we're going to use the plus for growth. Our rate is 6%. Remember, change it to a decimal, so divide it by 100. And then t is time. Initial amount, rate, and we want to calculate her initial salary, or her salary after t years, her amount of salary. And so this is going to be the equation that we're going to use. So plugging the numbers in, if we plug 0 in, 1 plus 0.06 is 1.06. To the 0 power is 1. And 1 times 40,000 is 40,000. Okay, so the next one, we're going to plug a 1 in here. So 1.06 to the first power is 1.06 times 40,000. So grabbing our calculator here. So 40,000 times 1.06. So year 2, $42,400. Okay, and then we plug 2 in for t. So this time we're going to have 40,000 times 1.06 raised to the, this time we're going for 2 years. And so she will have a salary of $44,944. Okay, couple last minute things before I run out of time is, you know that we have a growth if the base is greater than 1. Okay, growth, we know the base has to be greater than 1. For it to be a decay, and this is stuff you've probably learned in Algebra 1, the base is going to be greater than 0 but less than 1. And remember, when you're in this format, this number right here, when you're graphing, is your y-intercept. Okay, so I'm going to move this up a little bit. There you go. Okay, so if we were graphing this, we have a growth of starting at 40,000. So when you do your graph, you want your 40,000 to be down here. So I'm going to go, I'm going to make a little gap here and start myself off at 40K. And notice it's going up, not by a lot, so I think I'm going to go up by 2,000 increments. So 40, 42, 44, 46, 48, 50. And this is all in money. And this is her salary. And then over here we have time. 1 year, 2 years, 3 years, 4 years, 5 years. And then we start plotting our points.